So, today's topic is columns. Column or strut is defined as a member of structure which is subjected to axial compressive load. If the member of the structure is vertical and both of its ends are fixed rigidly while subjected to an axial compressive load, the member is known as a column, and for example, a vertical pillar between the roof and floor. Then what do you mean by strut? If the member of the structure is not vertical and one or both of its ends are hinged or pin joined, then the bar is known as a strut. Example of struts are connecting rods, piston rods, etc. So a column, it is a vertical member where both of its ends are fixed rigidly, which is subjected to an axial compressive load, and strut, it is not a vertical member while one or both of its ends are hinged or pin joined. Then failure of a column. The failure of a column takes place due to any one of the following stresses set up in the columns. They are direct compressive stress, buckling stress, and combined of direct compressive stress and buckling stress. Then there are two types of columns, long column and short column. So long column means a column is said to be long column if the length of the column is very large when comparing with the lateral dimensions. Otherwise, it is known as a short column. Then failure of short column. Failure of short column. Compressive stress induced is given by P is equal to capital P by A, where small p is the compressive stress and capital P is the axial compressive load and A is the cross-sectional area. That is, a short column of uniform cross-sectional area A subjected to an axial compressive load P, then the compressive stress induced in the column is given by compressive stress small p will be equal to capital P by A. That is axial compressive load divided by cross-sectional area. If the compressive load on the short column is increased gradually, a stage will reach when the column will be on a point of failure by crushing. And the stress induced corresponding to this load is known as the crushing stress, and that load is known as the crushing load. And the short column failed due to crushing. So, that is the failure of short column. That is, if the compressive load on the short column is gradually increased and a point will reach where the column failed by crushing, and we can say that the short column fails due to crushing. Next is a failure of a long column. When the length of column is large when compared to the lateral dimension, then we can say that it is a long column. Such column do not fail by crushing alone but also by buckling, and the load at which the column just buckles is known as buckling load or crippling load or critical load. And actually we can say that the buckling load is less than the crushing load for a long column. Okay, for a long column the buckling load is less than the crushing load, and actually the value of buckling load for long column is low, whereas for short column the value of buckling is relatively high. So we can say that for very long columns only very long columns are subjected to the buckling stresses only. Why? In case of long columns, the direct compressive stresses are negligible as compared to the buckling stresses. So we can say that very long columns are subjected to the buckling stresses only. So short column fails due to crushing and long column fails due to buckling. So these are the failure of long columns by buckling or bending. That is a buckled steel column and buckled RCC column. Next is the assumptions in Eulers column theory. The assumptions are, there are 7 assumptions. First one is column is initially perfectly straight and the load is applied axially. Second one is the cross section of the column is uniform throughout its length. Third one is the column material is perfectly elastic, homogeneous and isotropic and obeys Hooke's law. Hooke's law means the stress is directly proportional to strain within the elastic limit. Then fourth assumption is the length of column is very large as compared to the lateral dimensions. Fifth one is direct stress is very small as compared to the bending stress. Sixth one is the column will fail by buckling alone, and seventh one is the self-weight of the column is negligible. So the Euler's column theory deals with only long column. They will not consider short column. Euler's theory is studying with the long column only. Next is the end conditions for long column. In case of long columns, the stress due to direct load is very small in comparison with the stress due to buckling. Hence, the failure of long column takes place entirely due to the buckling or bending that we have already told. The following 4 types of end conditions of the columns are very important, and the 4 types of end conditions are: first one is both the ends of the column are hinged or pinned. Second one is one end is fixed and other end is free. Third one is both the ends of the column are fixed. And last one is one end is fixed and the other end is hinged. Then this we have to note. That is, for a hinged end, deflection is 0. For a fixed end, slope and deflection are 0. And for a free end, deflection is not 0. For a hinged end, deflection is 0. For a free end, deflection is not 0. And for a fixed end, slope and deflections are 0. So these we have to keep in mind for doing the problems all. Next is the expression for Euler's crippling load for different end conditions. That is the expression for Euler's crippling load for different end conditions. So we have already told that there are 4 types of end conditions. First one is when both the ends of column are hinged, the expression for Euler's crippling load P will be equal to pi square EI by L square. Second one is when one end of column is fixed and the other end is free, then the expression for Euler's crippling load P will be equal to pi square EI by 4L square. Third one, when both the ends of the column are fixed, the expression for Euler's crippling load P will be equal to 4 pi square EI by L square. Fourth one, when one end is fixed and other end is hinged, P will be equal to 2 pi square EI by L square. So we need to by heart all these 4 expressions for Euler's crippling load in order to do the problems. Next is effective length or equivalent length of a column. So what do you mean by effective length? Effective length of a given column with given end conditions is the length of an equivalent column of the same material and cross section with a hinged end and having the value of the crippling load equal to that of a given column. That is equivalent length or effective length or equivalent length of a column. That is, the effective length of a given column is the length of an equivalent column of same material and cross section. Okay. Let LE is the effective length of the column and L is the actual length of the column and P is the crippling load of the column. Then crippling load for any end condition P will be equal to pi square EI by LE square. So in this case, we have told that for different end condition, the different crippling loads are there. Then in common, we can say that the crippling load for any end condition as P is equal to pi square EI by LE square. So this is the showing different end conditions of a column, then crippling load in terms of actual length and crippling load in terms of effective length. The relation between the effective length and actual length. Both ends of the column are hinged. Then crippling load in terms of actual length will be equal to pi square EI by L square. Then crippling load in terms of effective length, what will be it? Pi square EI by LE square. We have already told that commonly for every end condition, the crippling load is telling in terms of effective length. So for every end condition, the crippling load in terms of effective length will be equal to pi square EI by LE square. And in this first condition, the crippling load in terms of actual length is pi square EI by L square and crippling load in terms of effective length is pi square EI by LE square. So what will be the relation between the effective length and actual length? LE will be equal to L. Then second case, one end is fixed and other end is free. Crippling load in terms of actual length will be equal to pi square EI by 4L square and crippling load in terms of effective length will be equal to pi square EI by LE square as usual. Then what will be the relation between the effective length and actual length? LE will be, that is effective length LE will be equal to 2L. Then both ends of the column are fixed. Then crippling load in terms of actual length will be equal to 4 pi square EI by L square. Crippling load in terms of effective length for any end condition pi square EI by LE square. Then for both ends of the column are fixed, LE will be equal to L by 2. One end is fixed and other end is hinged. Crippling load in terms of actual length is 2 pi square EI by L square. Then crippling load in terms of effective length, in common it is pi square EI by LE square. So the relation between LE and L for one end is fixed and other end is hinged is LE is equal to L by root 2. Next is the crippling stress in terms of effective length and radius of gyration. For this only the equation is need to be known for doing the problem solve. So here is moment of inertia can be expressed in terms of radius of gyration k, that is I is equal to AK square. Then we know that the crippling load in terms of effective length is P is equal to pi square EI by LE square. Then finally the crippling stress by the radius of gyration will be equal to, final value will be equal to pi square E by LE by K the whole square. So this equation is need to be by hearted only for doing any problem solve. That's not much important. Next is slenderness ratio. So slenderness ratio is very important. That is the ratio of actual length of column to least radius of gyration of column is known as the slenderness ratio. Slenderness ratio is equal to actual length by least radius of gyration, that is equal to L by K. Next is the Rankines formula. Euler's formula give correct results only for very long column, but what happens when the column is a short or the column is not a very long? On the basis of results of experiments performed by Rankine, he established an empirical formula which is applicable to all the columns whether they are short or long. And the empirical formula given by Rankines is known as the Rankines formula, which is given as 1 by P is equal to 1 by Pc by 1 by Pe, where P is the crippling load by Rankines formula and Pc is equal to the crushing load, that is sigma c into A, where sigma c is the ultimate crushing stress and A is the area of cross section. Then Pe is the crippling load by Euler's formula, where that is equal to pi square A by Le square, in which the Le is the effective length. Okay. Then if the column is a short, which means that the value of Le is small, then the value of the Pe will be large. Hence the value of 1 by Pe will be small enough and it is negligible when compared to the value of 1 by Pc. Neglecting the value of 1 by Pe from the equation, equation 1 by P is equal to 1 by Pc plus 1 by Pe. From that equation we can neglect the value of 1 by Pe. Then we can say that 1 by P will be equal to 1 by Pc or P is equal to Pc. Okay. So hence the crippling load by Rankines formula for a short column is approximately equal to the crushing load for a short column. Okay. Then for a long column, that if the column is long, which means that the value of Le is large, then the value of Pe will be small and the value of 1 by P will be large enough compared with 1 by Pc. Okay, that the value of 1 by Pe will be large enough when compared with 1 by Pc. Hence, the value of 1 by Pc may be neglected from equation 1 by P is equal to 1 by Pc plus 1 by Pe. That from equation 1 by P is equal to 1 by Pc plus 1 by Pe, the value of 1 by Pc can be neglected. Hence, 1 by P will be equal to 1 by Pe or P will be equal to Pe. That is, hence the crippling load by Rankines formula for long column is approximately equal to the crippling load given by Rankines formula. So, so what we have concluded, hence the crippling load by Rankines formula for long column is equal to the approximately equal to the crippling load by Euler's formula for long column. Then for short column, what is that? For short column, the crippling load by Rankines formula for a short column is approximately equal to the crushing load. Okay. So, hence the Rankines formula 1 by P is equal to 1 by Pc plus 1 by Pe gives satisfactory results for all the length of the columns ranging from short to long column. And by deriving the equation, that is 1 by P is equal to 1 by Pc plus 1 by Pe, finally we will get the value for Rankines crippling load. That expression for Rankines crippling load as P is equal to sigma c into A by 1 plus alpha into Le by K the whole square, where alpha is equal to sigma c by pi square E, and it is known as the Rankines constant. Okay, and sigma c is known as the Rankines constant. So this is the Rankines formula. So we need to study all this Rankines formula